Hello, welcome to this fourth video on the fundamental theorem of calculus. In the previous three videos, we explored the fundamental theorem of calculus part 1, where you look at evaluating a definite integral by finding its antiderivative. Now we're going to look at the fundamental theorem of calculus part 2. My name is Nakia. I'm happy to help you through this calculus journey. Let's get started. What is the fundamental theorem of calculus part 2? In some books or different places online, you might see these flip-flopped, but part 2 is going to be the following. If you have a function who is continuous on an interval from a to b, and then you have the integral on that function be the definition of another function, call the other function g of x. The t comes in as a dummy variable. So f is a function of t, it could be a function of w, you can put whatever variable you want in there, but it can be x. So you can't have x's inside the integral and an x is the bound. Look closely at the bounds. A is going to be a constant. It's going to be the left endpoint there, and then x is going to be the upper bound, and x is going to be changing. So x is going to start at a and then grow from a. X is going to be something that's smaller than b, and what this function does is it accumulates area. Okay, and so you give me x equals something bigger than a. We'll go with then this area between x and a will be what the function is. Let's say a is 1 and b is 5. So if x is 2, we want area from 1 to 2. X is 3, the area from 1 to 3, 1 to 4, and x will increase between a to b, and we're accumulating the area under the function. It turns out that this function defined by an integral is a continuous function. So long as the original function f is continuous. All right, well, also we can say that this function is also differentiable. We can take the derivative of it as well on the open interval from a to b. And then one more, the most profound statement is that the derivative of this g function, who's defined by the integral, is actually the original inside function evaluated at x. So to take this derivative of this integral function, all we need to do is replace the t inside the formula for f with an x. The value of a doesn't matter, okay? It doesn't play a role here. And so this is the connecting factor where you take the integral first and then you differentiate. You'll get the function back. All right, let's see an example. I have this function g of x who's defined as the integral from 1 to x on the square root of 3t minus t squared. Okay. And so x is going to be the upper limit. We have the function in there. Our job, find the derivative of the function. Well, according to the fundamental theorem of calculus part 2, all we need to do is replace the t, there's two of them, replace the t's that are inside of f with x. So instead of being square root of 3t minus t squared, you'll have square root of 3x minus x squared. These guys cancel each other out. These two operations are inverse operations. And you replace the t's with x's. That's it. You did it. This is the derivative of that integral function. Somebody gives you a function defined by an integral, and they ask you to take its derivative. You just replace the variable, the dummy variable, with the x. Okay? The lower number needs to be the lower limit needs to be a number. Okay? The upper limit needs to be the x. In our next example, we'll find that that's backwards. In the next example, we have the lower limit as an x. Sorry about that. We have the lower limit as an x, and the upper limit's a number. This is backwards. The way the integral is set up, the way the fundamental theorem of calculus part 2 is set up, is that you have to have the lower limit, who's lower than the upper limit, And the lower limit needs to be numerical, while the upper limit needs to be the x. And so with this being backwards, same thing as if it was, the upper was lower than the lower, we had to switch them and put a negative on it. Same thing, we switch them and put a negative on it. Now it's in the right kind of order to be able to take the derivative. And what we're going to, I'm in the way, I'm sorry. What we're going to do is replace the t inside with an x. And don't forget that there's that negative on the outside. So instead of cosine squared of 4t, it's the cosine squared of 4x. Okay, with the negative on the outside because we had to switch the bounds to be in the proper order to be able to execute the fundamental theorem of calculus, part 2. All right, let's do another example. In this example, we want to have the function at the upper limit to be something different than just an x. So my g of x function in this third example is the integral from 2 to 3x squared. And the formula on the inside for f of t is 4 over the square root of t plus t cubed. Okay, we want to find the derivative of this. So what we recognize then is that that's not just an x. That's more than just an x. And so we're still going to do the same process, but instead of replacing the t's with x's, we replace the t's with the 3x squared, whatever the upper limit is. But you can't stop there. We have to then multiply by the derivative of the function that's there. That comes from the chain rule. 3x squared's derivative is 6x. Okay, that's g's derivative. Why do we have to do that? Well, here's a quick little motivational explanation. Our derivative of our integral, we're going to set it up using d notation, d dx of the integral. And we're going to do a little substitution. If I was to let u be at 3x squared, then I'd have the integral from 2 to u. Okay. Now, if I want to take the derivative of that, though, I can't have d dx anymore. I have to have d du. So d du of that integral function, then I multiply by du dx. I'll end up with d dx. I'll end up with the derivative with respect to x by doing it that way. This Leibniz d notation is helpful. Remember, we did it for related rates, and we did it for the implicit differentiation. It's helpful to have this situation where you, instead of writing u prime, you write du dx. Okay. All right, great. What's the derivative of u with respect to x? It's 6x. So now that we have a single variable up top, we can perform the fundamental theorem of calculus part 2 the regular kind of way. Replace the t's with the u's, and then we remember now this other part comes in though from the chain rule. So we multiply by du dx, who's 6x. That's it. We can simplify it from there. Replace u with what u was, because we need the derivative back to us in terms of x. The function came to us in terms of x. We need the derivative back in terms of x. So just replace the u back with 3x squared. Okay, and this could be simplified actually. I wouldn't worry about it too much though. All right, great. Let's do one more. What happens if there are functions both in the upper and the lower limit? What are you going to do now? We need a number. Just like when we had improper integral from minus infinity to infinity, just any number whatsoever. Same thing. Any number whatsoever. And then we go from root x to 1, then we go from 1 to tan x. We put that number in there, any number, and then we break our integral into 2 separate integrals. If it's backwards, like the first one, we flip it and put a negative. And then to take the derivative, we're going to have to use a chain rule. Replace the t's with root x, multiply by the derivative of root x. Replace the t's with tan x, multiply by the derivative of tan x. So in my first step, remember I had that negative down front. I'm going to replace the t with root x. multiplied by the derivative of root x, which is 1 over 2 root x. In the second one, I'm going to multiply by, I'm going to replace the t with tan x, multiplied by the derivative of tan x, which is secant squared of x. Officially, you're done with the calculus, but there's some nice simplification that happens with this one. Let's take it another step. The root x's will cancel. That's good. Root x squared is just x. And so that's just going to be 1 over x plus 1. And then something nice happens on the second fraction as well. 1 plus tan squared, that denominator is actually secant squared. So we can cancel. And we end up with 1 over x plus, how the 2? Oh, the 2 came from the half. Sorry about that. 1 over 2 times the quantity of x plus 1. We'll negative that. And then plus tangent x. You did it. So be on the lookout for when the function's at the bottom, flip it and put a minus. Be on the lookout for when the function's more than just an x, chain rule, and be on the lookout for when there's a function on the upper limit and a function on the lower limit. Pick any number you want and break it into 2. All right, it's gone past 10 minutes. I'm sorry. Thank you for watching. This is the Fundamental Theorem of Calculus, Part 2. And this is the 4th video in our series. We have one more video coming. My name is Nakia, and please like and subscribe. Comment down below. Reach out to me if you need some help. And I'll see you in the next video.